Hey everyone. So in this video we'll be talking about arc length as another application of integrals. So far in this course we've seen two geometric applications. First is the area, right? We know that we can compute the exact area under the curve of a given function by first approximating it as this Riemann sum of n areas of rectangles, right? Where you're multiplying the height of each rectangle by the width, which is this fixed delta x. And as you take the limit as n goes to infinity, these rectangles get thinner and thinner, and you're basically accumulating all these infinitely thin line segments to get your area. A second application was that of volumes. And we also said that in order to compute the volume of a solid figure, well, we actually just need to know what the cross-sectional area is, right? Because now we're using these approximating cylinders, each of which has volume, area of the base, times the width of your subinterval. And so this Riemann sum up to n and the limit as n goes to infinity together means we're taking thinner and thinner cylinders until you can imagine it as simply taking infinitely many thin cross sections of the solid that you have to get the volume. So in this video we'll talk about arc length as a third application, and you'll see that it essentially mimics the method that we use for areas and volumes, in the sense that we're going to look for a way to approximate the length first, right? And then take infinitely many of those things as they get smaller and smaller. So how would we do that for this specific example? Right? This is the curve y equals 1/3 x cubed plus 1 over 4x. Starting from x equals 1, ending at x equals 3. Okay, so the first thing I'm going to do here is compute the coordinates of my points. This is 3, well, this is 9 plus 1 over 12, so that's 109 over 12. This one, and then the y coordinate is 7 over 12. And now, again, what I'd like to do is to compute the length of this arc here, right, of this curve, but we need to, or we want to get an approximate first. So what is my approximation going to look like? Well, remember that from calculus or from differential calculus, your derivative at a point, right, on your function gives you the slope of the tangent line at that point. And so if I were to compute the derivative at x equals 1 of my function, well, the function derivative is x squared plus, well, minus 1 over 4x squared. And so I plug in 1 into this formula and I get 3 over 4. And that's going to be the slope of this tangent line. Let me draw this again. Oops. There. And it's not the greatest approximation, right? But it's reasonable. So let's try computing the length of this line segment. And now you're probably wondering, how do we get the length here, right? Don't we need to know the coordinates of this other point and then use the distance formula? Right? So, I mean, you would be correct if you thought that. If this were the x coordinate x0 or x0, and this is the x coordinate x1, so we know that the difference in x is just going to be x1 minus x0. How about the difference in y? Well, we know slope is just change in y over change in x, right? So this is delta y, and it's equal to m times delta x. Which means this hypotenuse here, by the Pythagorean theorem, is equal to x1 minus x0 squared plus m squared x1 minus x0 squared. And I can actually rewrite this to make it a bit simpler by factoring out this x1 minus x0 squared. Right? It just becomes the absolute value of x1 minus x0 times the square root of 1 plus m squared. Or if we know for sure that x1 is to the right of x0, then this is a positive value, and we can just put parentheses. So it turns out we only need three things, right, to compute the length of this segment. We just need your x coordinates, where you're starting and where you're ending, and the slope. So for this particular line segment, we could say the line segment has length equal to change in x times the square root of 1 plus m squared. And whatever that is, that's the length. So okay, again, that's a reasonable approximation here. But let's go one step further, right? Similar, again, to what we did for areas and volumes. So what about if we do this and slice the interval from 1 to 3 into two subintervals, one from 1 to 2 and the other interval from 2 to 3. And instead of using that single line segment that spans the whole interval from 1 to 3, why don't we use one line segment for each subinterval that's determined by whatever the slope is at the left endpoint. Right, so in here we need to know f prime of 2, and plugging it in here, it's 4 minus 1 over 16, so that's 63 over 16. And you'll see here that this is a better approximation, right? It looks like a better approximation instead of using that single line segment a while ago for the whole interval from 1 to 3. And so here, our line segments have a total length of, so we get the length of the first segment first. So again, it's change in x, right? That's really just your delta x here, right? It's the change in x times the square root of 1 plus m squared. So it's 1 times the square root of 1 plus 3 over 4 squared. Plus, for the second line segment, again, it's 1 for delta x times 1 plus m squared. And this is a much better approximation. And you probably see where I'm going with this, right? What happens if we increase your line segments, or the number of line segments? What will that look like for my curve? Right, so say this is the curve I'm starting with, from x equals a to x equals b. Well, what's going to happen is you're going to get many small line segments that sort of follow the tangent line from the left endpoint of each subinterval to give you an approximation of the length of the curve in that really tiny subinterval. Okay, that last one wasn't really accurate there, but you get the picture, right? There. So it's going to start going down, and so on and so forth. And so how would we describe this using a sum now? Well, if we had n subintervals, really what's happening is just we're adding these guys together. right? It's just, again, delta x times 1 plus the slope. And what's the slope? It's f prime of 1, of 2, right? So we're using the left endpoint. But, I mean, instead of writing all of that, I'm just going to write xi star here, where we understand xi star to be the left endpoint. And so this is what's going into my sigma notation. Which means when I take the limit as n goes to infinity, what I'm going to get here is now the integral from a to b of, so what's the function here? This is the function with xi star in it. Delta x becomes your dx on the right. And what we have here is now the formula for the arc length of a curve, which is this. And note that this formula, we're assuming here that your curve is nice, in the sense that you have a continuous derivative throughout this whole closed interval from a to b. So, well, why don't we apply this to our previous problem, right? So here's the same problem on the new page. The arc length is just integral from a to b, the square root of 1 plus f prime of x squared dx. Okay, so that's a, right? That's b. What's f prime of x? Again, it's x squared minus 1 over 4x squared. Therefore, by our formula, the arc length is just the integral from 1 to 3 of the square root of 1 plus the derivative squared. And now you just have to evaluate this integral to get the arc length. And I'm going to let you do that yourselves. So please try doing it in your notes.